Welcome to the fourth and final night of the 2021 ALTAZ workshop. I've been thinking of tonight as Big Scope Night. As you can see from the agenda, the smallest scope that'll be mentioned tonight will be a 30-incher. So I think that qualifies as Big Scope Night. We're going to start off with the 800mm project, which I think everyone will find very interesting. Michele Scotti is going to walk us through the project he and three others have been working on. We'll follow that up with Tong Liu talking about his 40-inch 3.3 folded Newtonian. Mel will give a second presentation on all of the big glass and telescopes he's working on. And we'll end up with Dan Gray giving us an update on the 36-inch telescope he walked us through on the design phase last year. So with that introduction, I'll turn it over to Michele. Am I saying it right, or did I forget how to say it?
Perfect.
Oh,
perfect.
Okay, very good, close enough.
Spot on. Let me see if I can share. Do you see my presentation?
Yes.
Let's see if it works in presentation mode as well.
Yeah, looks good.
Excellent. Okay. So my name is Michele. I'm really honored to be able to present this 800mm telescope project tonight. Let's get started right away with the team, a team of four. Charly is our senior master glass pusher. Then we have Marco and Paolo that are basically doing the heavy lifting, and myself. Charly is actually pivotal in all this endeavor because he's the guy that you see in this picture. I think he ground kind of 100 mirrors in his life, and he went up to 500mm of aperture. He actually had 3 telescopes. Now he owns only one, and he has always thought about the next step. So going something more than 500 toward 1 meter aperture, right? So it's always thought, and as soon as we got into the conceptual phase, we said the mount is our Achilles heel. As a matter of fact, the one that you see in the picture, his personal scope, is struggling to track for more than 10-15 seconds. So we say we need to get on a different league here. So where to start? Where to get the blank? How to model in CAD resources, fundings, and I'd say that a good place to start is with being clear with the intention of this project. So the mission that we stated for this project is to build a proof of concept, so a kind of prototype, attainable or DIY friendly platform or imaging system capable of doing science and to be then shared as an open source. This is to close a gap that we identified. Is on the left is what you can see as a representation of, let's say, a pinnacle of amateur astronomy. You see a lot of talented people that are taking amazing picture, and usually they go up to 16 inches, 400mm. And then on the other side, you have the pros. You have observatory class telescope, meters and above. And there's a kind of a gap in the middle. So what if we are building a telescope to validate a sizable imaging platform? What if we then provide all the drawing, CAD models, and the process description? What if we take away the second guessing and so people can rely on a validated prototype? My vision. my vision is that of a success is that a bunch of guys in Australia, a university in India, a capable amateur astronomer in Germany can do their own version. They can tweak the design as they want, but on a validated platform. That is the intent of this specific project. And what you can do with that, to me, is with a robotized large telescope, you can collect a lot of scientific data that you can give back to the scientific community. Sure, you can take nice picture. Of course, you can use it for public open nights, a lot of different stuff. But to me, it's more like you can actually. What if we can tap into maybe 1% of the amateur community and start collecting scientific data out of that for novae, comets, exoplanet, transit, spectroscopy. You know probably way better than me. So how to do that? We lay down the technical feature of this project, and 8 of these. Like the mirror is an 800 millimeter mirror of 31 inches with a focal length of around between 2.5 and 3 meters. Is kind of flexible, the project itself. It is an Altaz mount. To me is the obvious choice. It has to have a fairly sophisticated tracking system. So that means a drive that is based on SciTech2, plus encoders. For these, needs to be transportable, or that kind of transportable you want to build and leave it in a place and forget about that. A 4 inches focuser, because we say, why not? Let's make it big. And since it's an Altaz, we want to make it as an imager. It needs to have a rotator and a guider included that are combined in a single piece with the focuser. All right. So let's have a little bit of disclaimer, so to speak. What this project it is absolutely not. So it is not the best, meaning that this is not a unique recipe. It is a lot of different ways to do that. And by the way, I would do things in a different way if I had to start from the beginning, different technical solution and stuff like that. It is not a professional tool. It doesn't want to compete with commercially available solutions that are out there already. This is not a plug and play so with a team that is setting it up, and you can forget about that. It is an amateur system, so it needs a lot of care, probably also running it. And third point is not cheap. It is affordable. We want that to be attainable. There are some data that I will show at a later stage, later in the slides. It's labor intensive, even though it's for free in the amateur world. But there are parts that are actually not absolutely cheap. But we're trying to find a way to make it as affordable as possible. So let's get back to the project, or actually what I think are actually 2 different projects in one, because of different expertise involved and different timelines somehow. So it is, you see on the left, the mount with his own challenges, and on the right, the mirror. So there are also 2 different parts of the team that are taking care of the 2 different things. But they two both integrate holistically, because if one of the 2 fails to meet the specification, the whole thing doesn't really work completely. So let's have a look at the dimension of this telescope, just to have a taste of what is this. Starting from the bottom is the azimuth table is 1.2 meter wide, so fairly robust foundation. And as of now, in this configuration, that is the one the picture is, I think, is a 3.75. It is slightly higher than 3 meters in total. So you will need 3 or 4 step ladder to have a look at that. But in my mind, it's like I really want to have my mom being able to look at the eyepiece if she wants, and not being too scared to fall from heights. What I call project ethos here are the guidelines that we want to stay with us while we are taking decision on design of this project. So when I say no trails means that everything needs to be there for a reason. When we are taking decision on the design, it doesn't need to be something that doesn't need to be there because we like it, or because it looks good, or because we have always done that way. It doesn't need to be a reason to be for a feature to be there and done in a certain way. And we can tap on some modern tool like FEA, or there's a lot of stuff that you can utilize to have your decision driven by science and by data. So kind of form that is following function at a certain extent. And of course, it needs to be DIY friendly. I keep highlighting that and underlining that because it needs to be a key aspect of the project. So let's now have a look at a little bit of some of the actual parts, because so far it's like a lot of CAD models and so on. Is this actually real, or there's something going on? And these are just random picture of parts that we have manufactured so far. I'd say starting from the top left, you can see a 27-point mirror cell with it's not fully completed. You see the wiffle tree on the bottom. Then going in the central part, you see the hexagonal upper telescope assembly is almost pretty much finished. Under that, you see the azimuth table, and you can probably guess on this 1.2 meter platform, you see a rail, a stainless steel rail that is part of the azimuth bearing. On the right, you see a CAD snapshot of the system that is actually the focuser, the guider, and the rotator all together. Below that, you can see the dry run of the assembly for the lower telescope assembly is pretty much done. And the legs at the very bottom, the legs of the, I call it tripod, is the legs on which the azimuth table is sitting on. And you might guess that at the end of this leg, you see bearings. There's a bearings assembly, so that the entire table is rotating onto that. There are 4 different areas that I hold dear in this project that I think are key for the success and the completion of this project. In processes that are elementary, even though complicated. There's a little bit of a contrast here, is that, but this gives me a chance to spend a few words on the fact that I really wanted to have in my mind process that are giving the chance to anybody around the world to go to something like a Home Depot, getting material that is ready available, and utilizing that in a smart way, and be able to build something that is accomplishing the target here. On the right, you see the structure with an holistic view. So effectively, we spent a year and a half, if not more, just on the CAD, and then routinely going through the analysis with the FEA and other stuff like that, just to make sure that we're starting with a design that really stands a chance to do what we want that to do. encoder snooping on plane wave. This is really was like definitely a good advice from the community here. Is like an encoding system that can be reliable and then can do the job here based on a Renishaw system in this case. And the mirror that is a project by its own, you will see at a later stage. I have 3 slides here on processes that are, to me, key for this project, meaning that are key for success in light also to be able to be implemented anywhere in the world. So this is, for example, is the azimuth table on the top, and it's like sandwich. Huh? Like, so how do I take poor materials and make something that is robust and light at the same time and affordable? So here you have like maritime grade plywood, and they sandwiched and glued together with that kind of foam that is that insulation material that you find on your ceiling usually, and then you can get in this configuration you can turn fairly poor material into something that performs very well. On the bottom is just few picture of the process involving the what I call the Pac-Man, is like the trunnions. So this is a sandwich as well. And on top of that, because when we were thinking about the design, we really need to think things in advance. You see that there are cutouts in the foam where we put some insert of wooden insert, so that when you have an anchoring point or when you have bolts and so on that are going through that, we really don't want to go through foam, but something more robust. Second process here, a little bit tricky and with a funny description. So we don't have a CNC. We don't want this project to be close to any CNC shop and so on. So we go from computerized numerical control to actually human analog control. So let me explain here a little bit. What you see in this picture is my attempt to build a grinding machine, a rudimental grinding machine on the Pac-Man, so on the workpiece itself. In this specific case is to grind the rails on the perimeter of the trunnions, so that when the entire telescope swivel on two ground bars, that is a fairly common design in this kind of telescope. You actually have a fairly precise surface, and you're going to make the life of the guiding system, the auto guiding system, much easier. So here the attempt is really to reproduce a kind of a huge bearing, but within, I wouldn't say microns, but with a tolerance that is making the life of the bearings the life of the auto-guided very easy. Next process is bonding, a new way of joining things. And again, I don't want to be close to a weld shop, because a guy in the Philippines, a guy in Argentina, a guy in wherever you want in the world, you might not have access to a nice welder. And in this case, you're maybe welding 1.5 millimeter thick aluminum that, I don't know, that translates in inches, something very thin. So to keep also the cost and the weight very as low as possible. And if you use epoxy in a specific way, as we're talking about aluminum here, you can build structures that are very light and at a cost that is minimal, and without the need to go to a shop that is able to weld, and in this case professionally welding very thin walls. Structure. This is something very tricky and interesting at the same time. I could spend hours and hours to talk about this, but I'm kind of proud to say the design is validated through FEA, so finite analysis. The main parameter is that the structure needs to be light and rigid at the same time. There are kind of two things that are in contrast. In engineering, usually, if you want to have something that is robust, you add material, but then it's adding weight, and then the performances of a structure like a telescope that degrade very rapidly. There are a lot of studies on white books for the VLT and other huge project. The FEA is usually an integral part of the design process here. Of course, what you see is wobbling is an exaggeration of one of the natural frequency of the telescope. Is absolutely a key element for the design. On the right, instead you see a deflection analysis. So with the payload or the cameras and filter wheels and whatever you're putting on the eyepiece at different angles, what is the deflection of the telescope? It is within an acceptable tolerance. And on the bottom right, you see a stress analysis. Very interesting if you want to lightweight your design. So that color map is telling you the material that is not doing anything, is not contributing to the stiffness or the robustness of your structure. You can easily cut it out and save some weight here and there. Encoders, this is really, really key for the tracking ability. It's a little bit the oxymoron here is that encoding and attainable are usually something that I always find out being in contrast. If you go to any show and you try to buy a system that is capable to do that, so with at least 10, 12 million ticks per revolution, it is something that is going to cost you, so going to set you off a couple of grand, at least probably 3. You can get something like that in an amateur way somehow. And in this case, my route was buying a couple of encoders from a scrapyard in the Philippines for a total of 150 pounds. And buying a reel of the optical tape. This, I think, is coming from a surplus warehouse in the US for probably 300 bucks. And I tested that with an oscilloscope that I bought as a kit from eBay, 20 bucks. Sold it all together, and I was able with that to check that the encoder coming from the Philippines and the optical tape that it was coming from the US, they were working together. Finally, see the tutso signal there. That is working on my table. The next step is to make it work as a system integrated in the telescope. But again, this is absolutely key, and it is basically very similar specification to the plane wave design, thanks to Dan. Mirror, that is the heart of the telescope, of course, is on a side project is given to our senior member of the team. It is an iterative side project as well. We started with a fairly thin piece of glass because the guy really wanted to jump on that and doing something. They couldn't stand still, but it is an evolving thing. So I think we're going through different steps here. I've ordered from Andre and I received a meniscus. So that is a little bit where I would like to go for the full completion of the telescope. But what I'm putting together here are some features that I think are making all of these affordable and viable to a certain extent. So silvering is a big thing to me. It's really like a game changer for this kind of diameter. A fast design here is like a bracket because the project is scalable, so you can actually scale it a little bit down to 500 millimeter or 20 inches. You can go up to probably 40-45 inches, and just the design itself, when it's proven at 800 millimeter, I think is gonna work as well. And meniscus is because I think is the new path for large builds, and I think Mel is gonna give us some update at a later stage. One of the last few slides here is that where we are at. I have a bill of material with a progress bar for each and every of the components, and I don't like to throw estimation how long it's going to take to complete and so on. So I'm going to use something objective and mathematical. So that bill of material with a progression bar is telling me that we are overall at 81.2%. So there's stuff that we still need to do, but most of the components and so on are completed. And kind of amazing because I don't really look at that very often, but the total bill right now, clearly excluding time, is less than 3,000 euros. I think all in all, adding also the cost for a couple of iterations for the mirror, I think we're going to stay within 5,000 or 6,000 euros. I think I'll be interested to see where we are landing with that, which I think is a fairly good proposition in the end. Next step is once we're building the telescope is to validate that, meaning that I have a FE analysis that I base the design on, and I have means to check the structure and see if the model frequencies of the actual structure that we build are correlating to that, and it's going to be a key aspect of the final stages of the build. I have in mind to simplify the design. There are a few things that can be done in a simpler way, I think, and probably in a even in a cheaper way. For example, the encoder system that are now on the marketplace, a fairly good alternative to the Renishaw encoder. And we need to find a home. So the idea is to validate that in the place where we are building this project that is in Italy, but in a absolutely horrific place to do astronomy because there's a lot of haze, a lot of fog even. So we're going to validate the project there, this telescope there, and then we're going to find a place probably up in the Alps or in the Apennines, some place maybe run by another astronomy club that they can take care of the telescope and making it run it. And because anyway, this is going to be fully remotized. Fourth and last point, but actually something that I really hold dear is to make everything open source. Is a little bit a personal thing because I learned so much from the astronomer community in all these years that I've been into this hobby or passion. So what I like to do is to document processes in terms of the description, fine-tune the CAD, generate all the drawings, and provide everything as an open source so that, again, these guys from all over the world, if they want to get into this endeavor, they can have a reliable source of information, and they can tweak the design to their own needs and do exactly what they want. Last slide is a thank you. That is not just your standard slide of thank you, is really thanks to most of the guy in connected to this call and in this community. Really gave me a lot of inspiration. There are countless hours that I spent looking at pictures from various websites, trying to figure out what is the nice design that were put in place, design solution that were adopted on various amateur build. I was really like the list of people that I would have to thank in person is actually too long. But to me, it's like this project is, I'd say that it's not a novelty at all. There's nothing really completely absurdly new. It's more like putting together a lot of different elements that are, I think, are not mature to condensate into a platform capable of imaging, and that can do something for the scientific community as well. And that's all from my side.
Thank you so much. Very, very impressive. Yeah, I'm really, aside from all of the technical points, what I'm impressed by is your dedication to making this open source. So anyone around the world can duplicate to some degree your success. This is a fabulous project. And I'm really glad that you were able to present it to us here tonight.
Thank you for your attention. And again, what I was saying is that we might fail. This is like something very new for us, but we put a lot of energy. We kind of push a little bit the envelope, and it might be an inspiration for something smarter than us to pick up this kind of project and take it to completion. So I think it's good to give it back to the community and say, look, do whatever you want with that, and if I can help with some consultancy, let's put it this way. Otherwise, it's really up to grab for everybody.
So at the very beginning, you talked about the 3 other people on this project, and that it's all Charly's fault. So yeah, so Charly is your optician, and
yes.
And so he's the one who's making the 800 millimeter mirrors, and he's making 2 of them. Is that right?
Well, the first one actually is done. It clearly was like a pathfinder, because we started with I think a 1-inch thick piece of glass. So it was really to take the rust away from the grinding machine and getting on with some work, because the guys were so excited and they really wanted to do something. But in the meantime, I ordered a meniscus from Andre from Canada. I actually received it this summertime, but I really need to complete the telescope mount first, so that we can first test the first optic that we have, and then we're gonna go on with the meniscus.
Okay, so I have a question from Mel in the chat. He asked if you can describe the team. How close together do you live? How often do you meet?
Nice question. So we are all from the same small hometown in Lombardy, northern Italy. That, by the way, only if you're fond of violin makers, because it's the hometown for Stradivarius, or Strads, as you say in the US. Unfortunately, I've been living in the UK for the last 7.5 years. So effectively, we try to, with the modern tools of communication, we try to stay in touch, do small pieces of work, and then when I go back, because it's a 2 hours flight from here, from UK to Italy, we usually carve out some time to progress substantially the project. Clearly, me being abroad is not helping. And but that's okay. We're not in a hurry. We're gonna get there, and it's really just a matter of time.
Okay, so we have another question. This one from Dan. He wants to know, how will you mount the motors, and will there be gear reducers or belts?
Oh,
friction drive?
Yeah. For some reason I left it out, but so that's an interesting thing. So I'm leveraging the fact that there's a friction gearing somehow. So the Pacman, for example, is a 1.2 meter friction drive to the ground bars. So that offers already 60-to-1 ratio. That is a friction drive. that is totally against backlash, because that to me is like the concept here is to keep backlash, that is our foe, as at bay as much as possible. I have sourced and refurbished a couple of harmonic drives. I think they are 100-to-1. And there will be probably a final step, that is the one closer to the motors, that is a 2-to-1 with belt and pullays, probably with a tensioner. And I'm taking off the gearbox from the Pitman motors, because that is a cascade of few gears, and there's a lot of backlash in that gearbox. So I'm taking it, I'm throwing it out. I'm just keeping the motor, and then there's a 2-to-1, 100-to-1, and a 60-to-1 that should be okay for this kind of application, and virtually backlash free or something like that.
Yeah, you should do really well with the harmonic drive reducers. I use those on my 28-inch. And they work perfectly.
Good to know. I studied some technical specification. They are known to have a little bit of a periodic error, but is really fairly tiny, the one that I have, and they are anyway before a 60-to-1 final ratio. So I've calculated that should be totally negligible to the overall performance.
Okay. Very good. Anyone else out there? Okay. Dan looks like he wants to say something. I'm not sure. Oh, he's talking to somebody else. Okay, so never mind, Dan. Thank you very much, Michele. Really inspiring. And again, thank you for being part of our program tonight.
Yeah, thank you for your attention.
Very welcome.